Hi, welcome to your Mac 200 Statics online classes. Today we are going to start chapter 6 of the textbook, in which we learn how to analyze engineering structures using several methods based on the solution of the equations of equilibrium. I hope you enjoyed this video. For this chapter, we have two main objectives. The first objective is to show how to determine the forces in the members of a truss using two methods, the method of joints and the method of sections. The second objective is to analyze the forces acting on the members of frames and machines composed of pin-connected members. Several structures designed by civil and mechanical engineers use trusses as the main structural component. A simple truss is a structure composed of slender members joined together at their endpoints. The members can be made of either wooden struts or metal bars. In particular, trusses often used to support roofs and bridges lying in a single plane and are called planar trusses. In both cases, external loads are transmitted to the truss at the joints, as shown in the figure here. In a roof, for example, the load is transmitted to the truss at the joints by means of a series of purlins. In the case of a bridge, the load on the deck is first transmitted to stringers, then to the floor beams, and finally to the joints of the two supporting side trusses. Since we have all the loads acting on the same plane for both cases, the analysis of the forces developed in the truss members will be two-dimensional. In order to design both the members and the connections of a truss, it's necessary first to determine the forces developed in each member when the truss is subjected to a given loading. To do this, we will consider three important assumptions. First, we will assume that all loading are applied at the joints. In most situations found in civil and mechanical engineering structures, this assumption is true, since the weight of the members is neglected because of the force supported by each member is usually much larger than its weight. Secondly, we assume that the members are joined together by smooth pins. In real cases, the joint connections are usually formed by bolting or welding the ends of the members to a common plate, called a gusset plate, as shown in this picture here, or by simply passing a large bolt or pin through each of the members, as shown in this other picture here. Just for simplicity, we can assume that these connections act as pins provided the center lines of the joining members are concurrent. Then in the last assumption, which is a consequence of the first two assumptions, we assume that each truss member will act as a two-force member, and therefore the force acting at each end of the member will be directed along the axis of the member. In other words, if the force tends to elongate the member, it's a tensile force T. On the other hand, if it tends to shorten the member, it's a compressive force C. In order to analyze or design a planar truss, it's necessary to determine the force in each of its members. We now learn the first method to do it, which is called the method of joints. According to this method, if the entire truss is in equilibrium, then each of its joints is also in equilibrium. Then, all we have to do is to draw the free body diagram for each joint and apply the force equilibrium equations to calculate the member's force acting on each joint. Those two equations are the only ones needed to assure the equilibrium condition of the structure. For example, let's consider the simple truss shown here, in which a 500 newtons load is being applied at the pin located at joint B. If we draw a free body diagram for this pin with the appropriate x and y coordinate axes, we have three forces acting on the pin, which are the 500 newtons external force and the force exerted by the truss members BA and BC. This free body diagram shows that FBA is pulling on the pin, which means that the member BA is in tension, and FBC is pushing on the pin, and consequently, the member BC is in compression. Those two forces are to be determined by the solution of the two force equilibrium equations. But now the question is, how do we know the sense of FBA and FBC before solving the equations of equilibrium? Well, in this example here, we can determine it by a simple inspection on the free body diagram. For example, we know that the 500 newtons force acting at the joint towards the positive x direction must be counterbalanced by some other force acting in the opposite direction. The only candidate for this task is the x component of FBC, which must be oriented towards the negative direction of the x-axis. The same thing can be applied to find out the sense of FBA. Since the vertical component of FBC will be oriented towards the positive y direction, the force FBA must be oriented towards the negative y direction to counterbalance this force and guarantee the equilibrium of forces at the joint B in both directions. If we have a more complicated case, or we simply don't want to do this inspection, we can always assume the unknown member forces acting on the joint's free body diagram to be in tension. In other words, the forces pull on the pin. Then, if the numerical solution of the equilibrium equations yields to positive results for the members, then the assumption was correct. If the result is a negative number, then the sense is the opposite as indicated in the free body diagram, and the pin is actually being in compression. Now, let's summarize the procedure of analysis of trusses using the method of joints. First, we have to draw the free body diagram of a joint always starting at the node having at least one known force and at most two unknown forces. This is very important because we have to limit the number of unknowns to the number of equations available to solve, in this case 2 equations. Next, we have to establish the sense of the unknown forces by inspecting the free body diagram as explained in the previous slide, or just assuming it and checking after the calculations are done. Then, based on the orientation of the x and y coordinate axis selected in the free body diagram, we have to resolve all forces into their x and y components, apply the 2 force equilibrium equations, solve for the 2 unknown members' forces, and verify their correct sense. Finally, using the calculated results, we continue the analysis for each of the other joints. Remember that a member in compression pushes on the joint and a member in tension pulls on the joint. Also, be sure to choose a joint having at most 2 unknowns and at least 1 known force. Now, let's demonstrate this procedure of analysis through one example. In example 6.1, let's take the same simple truss shown in slide number 5 and determine the force in each member and indicate whether the members are in tension or compression. As we did before, let's start the solution with joint B, since it has one known external load applied on it and 2 unknowns, as shown on the free body diagram. When we write the equilibrium equations for the forces in the x direction, we have that the 500 newtons applied force will balance with FBC multiplied by the sine of 45 degrees acting towards the opposite direction. By solving this equation, we find that the magnitude of the force FBC is equal to positive 707.1 newtons, which confirms the compression sense for this force that we have assumed in the free body diagram. For the second equilibrium equation, we do the same thing, taking all forces acting on the node in the y direction, which are the component of FBC that we just calculated, multiplied by the cosine of 45 degrees minus the force coming from BA member, FBA. After solving this equation for FBA, we find that the magnitude of this force is positive 500 newtons, which also confirms our assumption that FBA is tensioning the joint B. Now that all forces at joint B are determined, we repeat the analysis for the joint C. By drawing the free body diagram for this node, we figure out that we have the reaction force Cy coming from the rocker support, which is naturally compressing the joint, and we have the compressive force FBC coming from the member BC. We know that FBC will compress the joint C because of the third assumption listed in slide number 4. Since we have concluded that member BC is pushing on joint B will be pushing on member BC back due to the action and reaction law. This compressive force will then be transmitted across member BC to the joint C. Since we have already calculated the magnitude of this compressive force as 707.1 newtons, we can use it to calculate the unknown forces for joint C. The last force acting on the joint C is the reaction coming from the element Ca, FCA, which we'll simply assume here to be tensioning joint C, and we'll check the answer later. By applying the equilibrium equation for the x direction, we have that minus FCA is counterbalanced by the x component of the 707.1 newtons force, which allows us to solve this equation directly for FCA. And the result is positive 500 newtons. The positive sign here confirms our assumption that it was correct, that FCA is tensioning point C. Then for the forces acting in the y direction, we have that Cy is counterbalancing the vertical component of the 707.1 newtons force coming from the member BC, which results to 500 newtons. The last joint to be analyzed is the joint A, in which the free body diagram shows the reaction forces in the x and y directions for the pin connection support, and the tension forces coming from the members BA and CA, one acting in the y direction and the other acting in the x direction. By solving the force equilibrium equations in the x direction, we directly find that the support reaction in the x direction is equal to 500 newtons. And by solving the force equilibrium equations in the y direction, the support reaction in the y direction is also equal to 500 newtons. The results for the analysis are summarized in this figure. Note that the free body diagram of each joint or pin shows the effects of all the connected members and external forces applied to the joint, whereas the free body diagram for each member shows only the effects of the end joints on the member. And with that, we have finished the first part of chapter 6. Thanks for watching, and I'll see you in the next video.